welcome back. For our first talk in this session, we're going to be hearing from Emily Tour and Kabir Manandhar, who are going to be talking to us about introducing Potnia, a Python language library for the conversion of ancient texts to Unicode.
All right. Okay, hi everyone. So my name's Emily and I'm a PhD student in archaeology at the University of Melbourne. My area of research focuses on administrative documents from Bronze Age Greece and Crete, in particular using digital methods like 3D modelling, geometric morphometrics and phylogenetics to analyse those objects. However, I'm not here to talk about my PhD research today, but rather an adjacent collaboration that I've been working on with some data specialists from the Melbourne Data Analytics platform, including my two co-authors, Kabir, who's here in the audience today, and Rob, who unfortunately couldn't be here, but both have made an immense contribution to this Python library that I'll be introducing. There's my mouse. So our project, Ancient NLP, has been looking at ways of using deep learning techniques in researching ancient texts, particularly around exploring undeciphered or partially deciphered languages. However, we hit a few roadblocks early on in the piece and realised that there were some gaps in the tools that were available to researchers working with ancient texts. We've made some efforts to fill a few of these and one of those outputs has been Potnia, a Python library that enables the conversion of Romanised transliteration into Unicode text. If you're wondering what on earth that means and why it's important, hopefully I'll be able to answer those questions over the next 20 minutes or so. For a bit of context about the name as well, so Potnia isn't a fancy acronym or anything. It's the name of a somewhat enigmatic goddess who is referenced in administrative texts written in the Linear B script from Bronze Age Greece during the time of the Mycenaean culture, and was possibly thought to have been associated with slightly earlier Minoan culture in Crete. So on the logo, we've got the name Potnia written out in Roman letters here, of course, so that we all know how to pronounce her name, but also the corresponding Unicode symbols that spell that out in Linear B. So the signs Potnia, in just the same way that our library would convert it. Plus we have a pictorial representation of the Minoan goddess from a seal impression, who some scholars think might be Potnia herself. Our work on ancient NLP started from an interest in researching Linear B, as well as the undeciphered Linear A script used by the Minoans. So the name is just a bit of a homage to our beginnings, and I think she's pretty cool. So just to provide a bit of an outline for this talk today, so I'll start off with why a tool like Potnia is required, specifically why it's advantageous for some ancient language research to be done with texts that are actually in Unicode representations of the native script, such as Hittite cuneiform or Mycenaean Linear B, as opposed to just transliterated or transcribed data sets using the Roman alphabet. I'll then go on to compare current solutions that already offer this functionality to an extent versus what Potnia can offer. We'll then look at the specifics of... Oh, hang on, sorry, having a mouse moment, give me the sec. Yep. We'll then look at the specifics of Potnia's implementation, highlighting the key features that make it such a flexible, extensible, and hopefully user-friendly platform, particularly for non-technical linguists or archaeologists like myself. I'll then discuss some of the potential research applications of Potnia, including touching very quickly on what we've been using it for in ancient NLP, before finally wrapping it up with where you can access this application and how people can contribute. So starting out with some context, we've seen a pretty significant increase in the digitisation of ancient language datasets over the last decade or two, including cuneiform tablets in Sumerian and Akkadian or Hittite, Syriac manuscripts, Egyptian papyri, various Greek or Latin texts, Linear A and Linear B administrative and ritual inscriptions, the list goes on. And this amazing influx of digitised data is enabling a range of machine learning applications to ancient language research with some really exciting results, including advances in OCR, text restoration, automated translation, analysis of vector embeddings, and so on. However, a lot of these datasets only exist in Romanised transliterations, which is where the characters from a text, rather than being represented using the actual symbols of that script, are typed out using letters of the Roman alphabet. So we can see that here. We've got a Linear B tablet on the left. Yep, on the left. or my left at least, and on the right, a transliteration. So we've got the symbols R, te, re, te, R in the first word, and these have been spelt out phonetically in the transliteration. So we're able to sound out and comprehend the word more easily. Other types of signs as well, so we have ideograms, which don't represent syllables, but rather a whole concept. So these have been encoded with a Latin abbreviation, funnily enough. So we have the ideogram that represents a wheel. So you can see we've got that character used quite a lot on this tablet. It looks like a wheel. And that's transliterated as rota, even though that's nothing like what the word would have sounded like in Mycenaean Greek, because it's Latin. And then you have some other annotations. So we've got signs for word breaks represented as commas, changes in text sizes, forward slashes and quotation marks. We've got square brackets showing broken areas of the tablet. So texts in various different ancient scripts and languages are often represented in this way as a transliteration to make them more accessible for readers, or at least those who are versed in languages using the Roman script, so English, French, German, so on. It removes the need to rely on knowledge of a whole new script, encoding all that extra information in your brain, instead making the sounds and terms more familiar and easy for people to understand. This is often the state of play with the digitised datasets, even though we actually have Unicode blocks available for an ever-increasing range of ancient scripts. So here's an example of what the output would look like if we were using the available Linear B Unicode blocks, which I'm pretty sure have been available since the early 2000s. These types of datasets just don't exist online at the moment for a lot of different languages. Using these native script signs, it's obviously more accurate, but it does have some clear limitations if you are trying to read the text and aren't very well versed with that script. Transliteration, as we've highlighted, is important as an aid to comprehension and used widely as a tool to help learners of both modern and ancient languages. However, we argue that for certain applications of digitised ancient text corpora, particularly when you want to run the data through a language modelling process, it's less than ideal. This is because representing these texts as Roman script can introduce a lot of noise and ambiguity into the data set, which may affect the outcomes of any language modelling efforts. Some of this comes down to standardisation in the way things are transliterated, so there often is an agreement on notation systems, sign values can change over time as opinions change, and this can lead to artificial differences in data sets which are meant to be encoding the same information. Transliteration can also obscure important features of scripts, such as sign polyvalency, where a single sign is used to represent a number of different values. So transliteration will make it look like there's different symbols being used when that's just not the case at all. And of course, it can do the opposite, where one sound unit is represented by multiple different signs. That just won't be reflected very well in the transliteration. Also problematic is the use of encodings that draw on unrelated languages. So I've used the example from Linear B that we saw earlier, where the ideogram for wheel, which has been represented using a Latin word. The ideogram for wheel has been represented using a Latin word, which has nothing really to do with the Bronze Age Greek language. So these are all elements that would only serve to confound the training process of a large language model or one or a few data sets. Hence the need for a quick, accurate and easy to configure way to convert large transliterated data sets into their native Unicode script when undertaking such research. Now, we're definitely not the first to develop a tool for conversion of ancient text transliterations to Unicode. There's a number of great solutions out there, including Cuneiform, which is a facility for converting transliterations of Sumerian and Akkadian cuneiform. It has been used in a number of different implementations, such as the GUI depicted here. There's Unicode Converter, a PHP script that handles Egyptian hieroglyphs. There's the Anatolian hieroglyphs generation tool for Luwian texts, and palaeographic, a Python library for the converting Arabic transliterations. However, this currently available suite of applications does have some restrictions. They only tend to deal with one particular script or language, and many other scripts or languages out there just aren't represented at all in this group of applications. In the case of palaeographic, it only supports one of at least 6 or 7 different Arabic romanization systems. Some of the applications are made in a way that don't allow for easy contributions, particularly by linguistic experts who may not have technical expertise. And in the case of the Luwian converter, it's limited to only a graphical interface, so it's not really suitable for converting bulk amounts of text. We've attempted to bridge some of these gaps in the design of Potnia, which offers a more flexible, extensible framework for converting transliterations into Unicode. It's incredibly flexible in the way it can be configured, and it's therefore able to accommodate many of the complexities of transliteration, as we'll touch on in a moment. Also, we believe that it is a more accessible platform for contributors who might be domain experts, but not computer programmers. In terms of the implementation more specifically, Potnia has been implemented in Python, as expected, since I'm presenting here at PyCon, and uses an extensible architecture centred around the script class. So I'll go through a few of its key features, giving a bit more of an idea of how it all works under the hood. So each script that Potnia supports is configured via a single YAML file. This will contain a sign repertoire, as well as any regular expression rules that need to be applied during tokenization and regularization steps. So say if you've got some symbols that need to be stripped out, or some more complex signs that need to be handled in a particularly unique way. This unified structure simplifies updates, keeping everything related to one script in the same place, and it's easy to scale to new scripts. You just add a new YAML file. It eliminates the need for any hard-coded source files, which of course can get pretty messy. I've got the start of the Hittite cuneiform YAML file at the top right here, showing some of the mappings, and as you can see, it's all pretty clean and easy to implement. Below that, there's also an example of some of the regex rules that can be added for handling fringe cases. I think they're the linear B ones in that case. So if you import text into Potnia, whether that be a single word, as used in the example here, or an entire 10,000 line file of transliterated text through the API, the first step is going to be tokenization. So through our tokenized transliteration method, the input text is able to be split accurately into its meaningful components, which can then be directly mapped to Unicode symbols specified in the YAML files. As we can see for linear B, based on the YAML file, Potnia knows how to split the syllables according to the according to the hyphens in the transliteration. So it's put them into its separate tokens here. But this might be different for different scripts. So this is one of the things that, that can be specified per script in the relevant YAML. Also at this stage, if necessary, regular expressions and placeholders in the YAML file can be used to handle the tokenization of any special characters, any special character strings or spacing that don't follow the basic rules. Here we have the conversion step now shown at the bottom of the image, which is handled through the call method, taking those tokens from the previous step and converting them into the correct symbols as they are mapped in the linear B YAML file. So we've gone from the tokens here and we've got our Unicode down here as output. An optional component of the conversion stage is to regularize the outputs using an additional method, which we've imaginatively called regularize. So whilst tokenization preserves everything, there'll be certain elements that aren't mapped in the YAML files because they aren't actually part of the script themselves. Generally, these are annotations about features of the inscriptions and documents, as we saw earlier in this linear B inscription that I've put here, with the commas, quotation marks, forward slashes, and square brackets. Users may opt at this step to strip out these elements completely, or to replace them with wildcard symbols, perhaps in areas where the text is a bit uncertain. So that might be some damaged or broken parts of the text where you can't quite make out what the characters are. Again, this can be achieved through adding some relatively basic regex rules in the YAML file, and like so. Here the regularization is removed, the commas, whoops, I actually forgot to remove some of that, but the quotation marks and slashes, which are superfluous to the text itself. It's replaced the square brackets with percentage signs, which indicate that part of the text may be missing as kind of a wildcard sign. And this wildcard could then be used to indicate to the language model in a downstream task that there's uncertainty around the text there. This will be the form most ideal for tasks like language modelling, leaving only the native Unicode script with any of the noise introduced by transliterations and annotations removed. Of course, people may want to use Potnia for purposes other than preparing data as a language model input, so we've made regularization optional in the case that they'd rather preserve those additional annotations. And I want to emphasise again that these kind of regularization rules are going to be different for each script, So being able to manage them through a designated YAML file or through simple regex expressions is a much cleaner and more manageable approach than hard coding for each different script. In addition to YAML files for mapping, PyTest fixtures in Potnia allow for the definition of test cases as lines of YAML files. So we've got 2 examples here. These can be quickly and concisely added and a range of edge cases accommodated for in order to achieve full test coverage. At the moment in Potnia we have only 350 test cases for the handful of scripts we're covering and achieving 100% coverage with that. A final advantage that we want to highlight is the versatile interface options offered for Potnia. So you can interact with Potnia via a Python API, which is generally most ideal for instances where you're converting large amounts of text. However, we also have a command line interface, pictured here, with the transliteration and then the output. As well as a GUI, which we think looks pretty cute. The GUI uses Gradio, and at the moment it's possible to spin up locally on your computer and also generate a shareable link. So that's pretty much Potnia in a nutshell. In terms of the scripts currently covered in the implementation, we have Linear A and Linear B, as well as Arabic and Hittite cuneiform, which was a script used during the Bronze Age in what is now modern-day Turkey. We have plans to add many more as well, including Akkadian and Sumerian cuneiform, Ugaritic, Etruscan and Luvian hieroglyphs. Regarding research applications, we see Potnia as a valuable tool in the analysis of ancient texts. As we've highlighted, its extensibility makes it easy for researchers to add new scripts or to expand on existing scripts. This will allow us to supplement the existing transliterated datasets with additional ones in Unicode, which, as we've said, are more suitable for many machine learning applications. Potnia, Potnia therefore has a place as a pre-processing tool, which can then be used to prepare texts before they undergo language modelling. And these resulting language models themselves can support further analysis, including text generation, text restoration, and vector embedding analysis. This is something that we've done recently ourselves through ancient NLP with the entire Linear B corpus, converting all text in Unicode in Potnia before training a language model on the data, and then taking the resulting vector embeddings for each of the different signs and plotting them using a principal components analysis or PCA. Which is what we've been able to do here in 2 dimensions using the first 2 principal components from the vector embeddings. So we've got the different ideograms. They're a little bit small, but you might be able to see some of them. So they're those signs that represent entire concepts in Unicode, and we're able to plot them out visually and explore potential semantic or contextual relationships between the different characters based on the language model's understanding of them. So this can be really useful for languages where you're unsure about the values of potential signs, as is the case for several Linear B signs, or you're just wanting to explore the text for unexpected or interesting correlations that may be difficult to detect without the aid of machine learning. So this is a type of analysis that would be much more difficult without Potnia, not only because of the improvements that you get to the language modelling process, but also the ability to create graphical representations where visual and semantic elements of the script are brought together. So to wrap up, we made Potnia open source under the Apache 2.0 license, and it's currently available through PyPI and GitHub, along with supporting documentation. We'd love to have new contributions of scripts from the community under the Contributor Covenant Code of Conduct to help grow the value of this software even more. A big thank you to the wider team who are integral in bringing this project together, and the many people who assisted us with advice and expertise along the way, as well as the support of the University of Melbourne's research in computing services in making a lot of our research possible. And with that, I'll open the floor to questions.
Thank you so much, Emily. We do have some time for questions, and I can see a hand at the back. We have a roving mic.
Fingers crossed? Yeah. So I may have missed it, apologies if you covered it, but I think it's possible to represent, like there's not always one-to-one between script and language. Are there aspects of Potnia that allow you to handle that sort of difference?
Can you give me a specific example of what you were thinking?
Well, like old English, archaic English could have been represented in like runes or the Latin alphabet. And so if you were translating from a Latin source, you might want to know what language that Latin source is in to do the transliteration properly, maybe?
Okay.
I might be, I'm not an expert. I've just read stuff online. I'm like, hey, that's cool. So sorry if I mangled like all of that question.
No. I'm just trying to think. So the way we set it up, it's for individual scripts, and then you'd probably target the particular script you want it to convert into. And if there's specific rules for the data set that you're working with, you just need to make sure they're accommodated in the YAML file. So if the underlying language uses some specific things, you just want to make sure those exceptions are covered, whether that's through regex rules or that sort of thing. So, yeah.
Thank you.
I think there was a question over there, and then...
Sorry. Thank you, that was really interesting. Not knowing anything about ancient languages, how complete is the Unicode entry for those languages?
That's a really good question. Some are more complete than others. So we've been having a bit of fun with Linear B. Linear B has quite a few, I guess, what you'd call compound characters, where it's taken two and sort of smushed them together into one. The Unicode doesn't currently cover that, which is a bit frustrating. So we've had to come up with a bit of a workaround where we put the two together and have a plus sign in the centre and make that a single output. So at least, I guess, the language model's still going to see it as a single unit. Whereas Linear A, whoever did the Unicode for that did an excellent job of doing all the compound signs. So different levels of coverage. Something that you may have noticed isn't covered, or that we haven't included, is there are particular signs for numerals out there for the Aegean scripts. I think the level of complexity to get that into Potnia at the moment, we haven't quite wanted to tackle yet for a few reasons, but I think it's something we could definitely do. So,
just to add to that as well, the PyTest coverage, that's a good indication of how mature a language is. So as Emily said, Linear B is quite mature, and you can really look at through the PyTest, because there's a lot more tests for Linear B than other languages. And it's going to keep getting mature. Like there's still like we'd say a proof of concept work. And maybe in the next year, we'll add more languages, there's going to be more test coverages, and it's going to keep getting better.
And I think...
That was very much my question.
Okay. Are there any more questions for Emily and Kabir?
This is not a direct question for Potnia, but just say, for example, you had an image of a cuneiform tablet and you want to transcribe it.
Yep.
What's the steps in like loading those cuneiform like characters into like a script to be ready to be transcribed?
So at the moment, as far as I hope this answers your question correctly, at the moment, as far as I understand, there is some development of like OCR tools where you can take a scan of a cuneiform tablet. It'll go through character recognition. It does it to some degree of accuracy. I think they're still sort of refining that model further. That will then, it should be able to it can map it to a transliterated value, and it can also map it directly to a Unicode sign, and then it'll output the text to go with it. So there are tools around that do that at the moment, 100%.
Okay, thank you.
The cuneiform researchers tend to be pretty ahead in this sort of stuff. So
Yeah, but it might be something for us to explore as well. Right now, we're focusing more on transliteration.
So we're working with data sets once they've been digitised.
Digitised rather than in images, but maybe down the line we could
but
think
there
about
are
this as well.
there are people working in that space and doing some pretty cool stuff already. So I think,
Sorry, this is a very nerdy question, but I just wanted to ask how much of a corpus you have to work with for Linear A.
Yep. As in how large it is? Yeah. Oh, God. Brent's going to be so upset if I don't know this off the top of my head. It's a much smaller corpus, so I think it's about 1,200 inscriptions. So it's not a lot. And that obviously is going to present some problems when putting it through a language model to the degree it can learn. And that's something I think we're going to be doing next week. So
yeah, it's a really good question. There's some resources like the Linear XYZ and Sigla websites which contains these tablets for you to get an indication of how many documents can there be.
It's about 1,200 off the top of my
I
head,
think so.
whereas linear B is 6,500.
Yeah.
So they're quite different in size, and then cuneiform, it's just forever, millions of
Yeah.
characters and stuff. So
Yeah.
yeah.
This may be kind of a tangent.
Love a tangent.
Do you see these ancient NLP libraries or other libraries being able to help with language preservation?
I think absolutely. Yep. So I think one of the nice things about Potnia is, anyone can contribute to it. So people who are working with, I guess, preserving less well-used languages or particular texts, this kind of puts them into a digital form that immortalises them forever. And I guess texts are fragile things as well, the physical documents. So having these digital data sets is really important.
And I'm going to go on a bit of a tangent again.
Yes,
from
please.
This. So I work a lot with large language models and natural language processing. These languages are not represented enough in training these models. So through this process of digitization and making it open source, they're going to go through the training process. Like the models will see these data sets, it's going to be part of it, and they'll understand these languages more. It's very important for large language models to understand ancient languages and not just be focused on languages that we're using right now. Yeah.
Was there a question there? Or Clinton?
Does the transliteration of characters into Roman, of linear B or whatever characters into Roman characters change in like accent over time? And if so, how do you account for that?
How do you mean?
Like if a tablet was transcribed in a certain way in like 100 years ago, and the pronunciation or the understanding of the pronunciation shifted, does that?
So you just have mappings to accommodate for both scenarios. So and that's one of the things that we do think is a good advantage is you just add one more line of YAML and you can accommodate that shift in usage. And as I said, there are different transliteration systems out there, so being able to easily just accommodate those is really, really important. So no, excellent question.
So I'm a bit of a noob, so forgive the question. But with the progression of time, with the language changes, is that what the compounding is for that Potnia can handle, or is that a different set of problems?
How do you mean?
So you know how the language progresses over time, it changes.
Oh, so our understanding of it changes over time?
Or
even
language
like
evolves.
the language evolves, like even the English language, how once typewriting came in, it sort of solidified it, but before then it was sort of more fluid. Is it spots in time? How is that kind of handled with Potnia?
It's probably something we haven't considered in the way we've done it. So we've taken a pretty standard view of linear B, Hittite cuneiform, those types of things. Just trying to think how we would.
Maybe I can try a little bit. So we've got linear B, which is transliterated in a particular format right now. So it works for the current transliteration, Romanized transliteration process. Say like this changes. Not everything's going to change completely. So it's going to be easier for the next person to do it. They can look at the linear B as a language won't change, like the way it works. The transliteration, the Romanization might change, but they can always fall back on what's there and then improve on that, change that. They'd still create a new YAML file, but they won't have to start from the beginning. So that's the best part about Potnia, that, it becomes easier no matter what changes there are because there's baseline stuffs there.
And I guess if you... do we have to wrap up?
This is a fascinating
we can
conversation.
Have a
and
different
I think
conversation.
A massive tribute to this topic and how well it's been presented today. So if you could join me in thanking both Emily and Kabir once again.